welcome back to Find, Solve, Explain. Today I have Bmo2 2017 question 1. It's a rather fun problem with a few key realizations that really help you break it down. This problem concerns triangles which have vertices with integer coordinates in the usual xy coordinate plane. For how many positive integers, n less than 2017, is it possible to draw a right-angled isosceles triangle such that exactly n points on its perimeter, including all three of its vertices, have integer coordinates? The key for this question is to consider a few different possible cases. First of all, you can realize that the xy coordinate plane, with just the integer coordinates, can effectively be broken down into a series of dots with 1 by 1 squares. Now on to our triangles. If we take a look at a triangle, let's say that there are 3 dots on each line on its shorter side. We know that these dots have to be equally spaced. This is because if the dots were not equally spaced, then the vector from the shorter 2 dots together could simply be repeated again, and we would get a new dot which was on the line, but that would be a contradiction as there are only 3 dots on the line, not 4. This also applies to lines with a larger number of dots. What this means is we can always break lines down, as the triangle with sort of 3 dots on each line can be broken down into a triangle with 2 dots, or 1 length. The second realization, which is important to solving the problem, is that fundamentally there are only 2 types of triangles. The first triangle has only 3 dots. The second triangle has 4 dots. It's effectively made from combining 2 of the 3 dot triangles. However, this can seem daunting to prove. The way I like to prove it is using the vectors of these lines. Considering the vector of the shorter side to be AB, we know that the vector of the other side can be written as minus b, a. This is because these 2 vectors have to be at 90 degrees to each other. Now looking at the final vector, the vector of the longest side, this is a minus b, a plus b. We already know that each of the simplest triangles has to have shorter sides with 1 length between them. That is to say, there are no dots interrupting them. This means that there are no common factors, as any common factor between a and b could break up this in, let's say, a dot in the middle representing 2, or 2 dots representing 3. Therefore, a and b must be coprime. We now look at a minus b and a plus b. The GCD of a minus b and a plus b is the smallest possible sum of k copies of a minus b and m copies of a plus b. Therefore, any other sum of a minus b and a plus b must be divisible by the GCD. Now we can look at, first of all, taking k and m to both be 1. This means that the GCD has to divide 2a. Now we take k to be 1 and m to be minus 1. Or sorry, k to be minus 1 and m to be 1. This shows that the GCD must divide 2b. However, a and b are coprime. This implies that the GCD has to be either equal to 1 or 2. This is actually exactly what we saw earlier with these two cases of there either being one length between or two lengths. Now we simply have to look at how each of these triangles extends. The first triangle is relatively simple, as all you add is an additional point, which is sort of the intersection of these two, as the triangle of the scale 1 larger has effectively an additional row sort of forming like that. This pattern of adding 3 is incredibly easy to prove. The next triangle, if you imagine adding an extra space, we already know can be made of 2 of the smaller triangle, and the smaller triangle has 3 on the bottom. Therefore, this triangle must also have 3 on the bottom, an additional 1 for the other side. This started at 4, and ends at 8. This will continue as you then get 4, and then 4, and then 7, which in total, as you have to deduct 1 from each side as the points overlap, will then give you 12. As 15 minus 3 is 12. So, in other words, the triangle that starts at 3, each time you can add 3. Triangle that starts at 4, each time you can add 4. In other words, the number of isosceles triangles that it is possible to draw with endpoints on its perimeter, where all of them are vertices, have to either have n divisible by 3 or 4. This is just the number of multiples of 3 plus the number of multiples of 4 minus the multiples of 12, all of which are less than 2017. This number, I believe overall, comes to 1008. Thank you.